All right, hello, I'm William. I'm a senior PhD student from the Carnegie Mellon database group. I have spent most of my life, or most of my PhD life at least, really thinking about sort of autonomous DBMS systems, sort of database tuning in particular. And so today I'm actually going to talk about what we sort of view as like the next generation of like automated database tuning. And before I get into it, I just want to give like a quick about me. So I was a DBMS performance tuning intern for a summer in 2018 at NVIDIA. And then I worked on the execution engine at SingleStore for about a year or so in 2021. And I've been working or thinking about sort of self-driving DBMSs, tuning, since about like 2019 or so with Andy Pavlo at Carnegie Mellon. So in today's talk, I'm going to like discuss tuning in a bit of a chronological sense. So we're going to start in the past, focusing a bit on like what tuning is, why do we do this, the role that DBAs have historically played in this role. And then we're going to shift our discussion to the present, sort of with the main focus on a lot of these current automated tuning tools. And then we'll shift our discussion towards where we currently think the state of the frontier is with a single holistic tuner that can tune everything you want. And we'll then sort of talk about what the future holds, how these recent large language models sort of might play a role in this, how they might fit in. And so let's sort of start back in time. And I just want to sort of say, like, just briefly describe what exactly tuning is. And the tuning is sort of an iterative process of configuring your database system for a given workload. And as this community probably already knows, this process is extremely important so that you actually get good performance that you want. However, tuning is extremely hard. It's made harder sort of over time even, just because new versions come out every year. These new versions expose more and more options. They expose more things that allow users to sort of tweak, adjust how the system behaves to suit their own specific needs. And to just sort of illustrate some aspects that you can sort of configure these days, there are these sort of system knobs that control high-level system behavior. So this sort of includes how much memory is in the buffer pool, how your optimizer is behaving, how data is flushed to disk. And then there's sort of all these other different like physical design options, right? So this is a coarse notion of what indexes should I have in my system, down sort of all the way to how should each index may be configured individually. Do I want sort of like a B tree? Do I want a hash index? How packed should each page be? So all these sort of different variations. And there's sort of also numerous query options made available, commonly through various extensions like PGConf.dev. And these just take the form of various plan hints to the optimizer, runtime knobs. And they're really specified on like a per query, alternatively a per template basis that just alter how the system sort of executes the query when seeing it. And there's sort of a lot more options beyond just the limited amount I've listed here. The important thing really here to note is just that all these options, when you do sort of try to use them, tweak them, they can interact in subtle ways that make it difficult to sort of reason about manually. And in addition, when you do combine all these, you can get trillions of possibilities. And so historically, the industry has sort of relied on DBAs to sort of tune the system. And these DBAs are specialized in specific sort of systems. They reason about all these different possible possibilities, sort of understand how changing different parts impact other parts, how they impact the workload. And so they sort of use a lot of their domain knowledge, expertise, acquired experience to just ensure the system remains operational. And so I'm just sort of citing data from the sort of US Bureau of Labor Statistics. And they have noted that the number of DBAs has been declining in recent years, from around 86,000 in 2021 down to around 73,000 or so in 2024. And a part of this is also just due to the evolving sort of role and nature of DBAs over time. But another sort of explanation is also just that there has been recent sort of development of various like automated tuning tools to help this process along. And so to just sort of recap the past before we continue, hopefully I've convinced you all that database tuning is hard and has historically relied on DBAs to sort of optimize the system. And recently, the number of DBAs has been declining. And so this brings me now to sort of the present day, where tuning sort of involves combining a mix of sort of user domain knowledge, but also just like various tools from a growing sort of toolbox over time. And so the last decade or so has seen a pretty substantial like proliferation of various tuners. And these tuners are really specialized in sort of optimizing a specific aspect of the system in like reasonable isolation of each other. And so I'm not going to list every tuner under the sun. Mostly I'm just going to sort of give a sampling of like some widely utilized ones and some that are more academic prototypes. And so for tuning system knobs, there's PGTune, which I hope people are aware of, and AutoTune. For tuning your physical design, there is Dexter and Microsoft Research's Database Tuning Advisor. And then for query options, there's also sort of like Bow and AutoSteer, respectively. And the thing here to know is just that like every year at like SIGMOD or VLDB, the database conferences, usually there's some group or a few groups that will publish some new tuning framework, new tuner. And so this list really sort of just keeps growing over time. And so before I want to talk about how most of these tuners actually work, I'm just going to briefly sort of discuss what they actually consider. And at its core, each tuner sort of thinks about tuning actions. And these come either from the system itself or usually from the workload. And to sort of give an example of this, a knob tuner may read PG settings to just figure out what knobs does Postgres expose, sort of their type, what are the valid value ranges, it can like tweak, adjust. And an index tuner sort of may analyze the workload statically to sort of figure out, okay, these indexes are relevant, and then sort of use explain to figure out like, will this index actually even be used? And so each tuning action really just sort of describes some discrete change, some change to the system. You can alter the system's configuration. You can change its physical design. Or you can just simply change how the system should execute a certain query. And these tuners are, as far as we're aware today, usually run during an offline sort of environment. And this is mainly just for safety reasons. By using some offline environment that's not the production system, you can let the tuner freely try things. It can try to experiment with things without the fear that you might, like, for instance, drop an index that you shouldn't drop, and now the production system is just degraded. And so in this setup, really, the user first collects some workload trace that sort of encapsulates what is of interest. It is passed to some tuning tool. And this tuning tool really reasons over its set of tuning actions to suggest some configuration that's hopefully useful. And this configuration is usually then just deployed on the DBMS. And for some tools that do support it, the DBMS can optionally return some feedback back to the tool. And this cycle just repeats in a very like iterative process. Right? And we commonly obtain this feedback usually from just running the workload trace in some cases. If it's more transactional, you may run some benchmark instead to try and just estimate the configuration's performance. And so this feedback is just some indicator of how good this configuration is. So it could just be the workload's runtime, if that's what you're optimizing for. It could be transactions per second, if that's what you care about, and so on. And so, however, there are some limitations to using just individual tuning tools, right? And to illustrate this, I will use a join order benchmark. And so each tuning tool in this setup really just tries to minimize the workload runtime. And so for reference, this is the sort of stock deployment, if you may. So if you just untar a fresh copy of Postgres, you just boot it up, do no tuning, and run the workload. And then now I'll show sort of 3 bars. This is respectively the performance if you only tune your knobs, if you only tune your indexes, or only tune your queries. Right? So there's some modest improvement over if you just did nothing at all. However, as I sort of show here in these like hidden away boxes, it is possible to get better configurations. And if you sort of may think about it further, you can do that simply if we can tune over like essentially more parts of the system at once, right? So instead of just thinking about only knobs, maybe we should just sort of tune everything. And that brings me sort of to sequential tuning. Sequential tuning is the sort of subject of recent academic research that sought to more formalize what we may have like sort of the notion behind maybe you should always tune your knobs first and then always tune your indexes after, within sort of a more formal coordination framework. And so they take the approach of sort of, rather than building a single tuner that can do everything at once, they reuse existing sort of tuning tools that target disparate aspects of the system. And so sequential tuning then treats it more as like a scheduling or like a coordination problem. So it tries to figure out like, I have these tools now, what is the best way I can run them one after the other or interleave them, such that like if I simply compose what each tuner finds along the way, I will get something that's desirable. And sort of as you can sort of expect, there are different quote unquote like scheduling policies. You can do the simplest, which is just round robin. So you simply cycle through your tuners. So you first tune your knobs, then you tune your indexes, then you try some query tuning, and then you may come back and then do your knobs again, and so on. And there's also more sort of complex ones, which you pick the next tuner based off of some notion of how much likely it will actually benefit the configuration, right? So that's like a more benefit-based method. Despite the promise that sequential tuning might sound like, it does have sort of a noticeable flaw that's captured by sort of the prisoner's dilemma problem. And in a sense, what this really says is just that a tuner won't make a locally suboptimal decision, even though that might enable a future tuner at some future time to find something that's actually globally optimal. And to illustrate this, I'll sort of take the query 26C from the earlier join order benchmark. And for simplicity, I'll only show here the relevant like 2x2 grid. And so you have an index tuner on the horizontal axis that just decides between 2 indexes. There's a query tuner on the vertical axis that just decides between 2 hints. And each grid cell really just shows the runtime of the query under a given configuration. And so the main thing to note here is just that the bottom right is the best you can do. So if we sort of just assume that we start in this top left corner and that the index tuner will go first. So under this sort of world, the index tuner is really constrained by the fact that the query tuner is basically fixed to hint 0. So it only decides, do I want to try index 1 or just stay with my current index selection? So it tries index 1. It learns that it's not good because it worsens the query runtime. And then it just stays with index 0 at the end. And so then at the end of its round, it switches over to the query tuner. And now the query tuner, in sort of a mirror case, is sort of constrained by index 0. And so it just decides, do I want to try hint 1? It learns that once again it's not good. And so it stays with hint 0 at the end of its sort of round. And then so at this point, no matter how you keep playing it out, you'll just find that it's basically just stuck here, right? And so this is sort of just because that each tuner is tuning in isolation of each other, so that neither one is really aware that if they just end their round on something suboptimal for it, the next round the other tuner can just simply find something that's actually globally better. And so as a sort of teaser for where this is going, if you do have a single tool that can consider all possibilities, In other words, it can sort of navigate in some ways to all cells in this grid. You can sort of discover that there is a better configuration with index 1, hint 1. And so sort of back to this, to just remind everyone, lower is better. And so I previously showed here just sort of the runtimes if you only tuned individual aspects of the system. Here is what would happen if you then do sequential tuning. And so essentially the main difference is that whether you tune your queries first, which is the left of the two bars, or whether you tune queries sort of like at the end. So you tune your knobs first, indexes, and then you tune your queries. And as I've been sort of alluding to, the order does matter, just that if you do tune your queries last, you can get a further 50% reduction over tuning them first. And to sort of just recontextualize this relative to like no tuning, the default, tuning indexes gets you about a 2x save improvement. If you then tune your knobs, indexes, and queries in that order, you get about a 5x or so. And then with our sort of holistic tuner, Proto-X, you can actually get even better, which is about an 11x improvement. And so to just quickly recap this sort of section, tuning today typically involves using automated tools of some form or another. However, just due to the limitations of sort of individual tools or challenges involved in coordinating these tools when you sort of compose them together in different ways, there is sort of a limited improvement that you can obtain. And so that brings me to what we sort of currently view as like the state of the art, if you may, of like a holistic tuner that can, in some ways, consider all aspects of your DBMS together. So I want to sort of just start with a bit of a straw man approach to this, which is, what if we just try and combine like all aspects that we want to consider, everything, into some giant configuration space and like just try to tune that, right? And what that sort of looks like is that we will take all our system knobs, all values that they might take. We then just combine that with all possible physical design options. So that's all indexes, all variations for each index, depending on what they may be, and sort of like different query options for each query of the workload, and sort of so on. If you sort of might assume at this point, tuning this does not work well, you're very unlikely to really find a good configuration at all, nor will you be able to find it sort of reliably and consistently. And the reason for this is sort of twofold, right? One is just that there's just too many that you have to consider. And the second that sort of follows from that is just that few configurations actually perform well. And so trying to find something good in this entire space is sort of very similar to like finding a needle in a haystack. You just have to hope you get lucky. And so that brings me to like sort of our key insight to this. And the intuition sort of here is just that even though there's a large number of like unique quote unquote actions in this space, many of them can actually be related to each other in some way or another, assuming you have a given workload and sort of an environment constraint. And so sort of an example would be like maybe setting shared buffers to similar values of like 32 gigabytes versus 33. Another might be, for instance, building an index on columns A versus an index on columns A, B. And even though these two indexes are not the same, depending on what your workload looks like, what queries are in there, what the composition of them might be, you may find that the two of them might give something similar, even though maybe one is slightly better than the other. Right? And another example might just be setting the amount like hash memory a given table query can use to similar values. And the key point here I really want to sort of emphasize is just that there's the theoretical sense that you do have to try every action once just to learn is how it will actually impact my workload. But sort of if you have similarity, you can sort of start inferring how something you haven't tried yet based off of sort of observing similar actions to it. So like another way of looking at this really is like if you've observed how action A behaves, and you can start prioritizing or discarding sort of similar actions to it based off of sort of how A behaves. So if A actually help your workload, you may want to look more towards like actions that are like similar to A in some way. If A like basically it was like extremely harmful, then you can also just sort of like start ignoring actions that are also similar to that in some way or another. And so by doing this, you sort of end up shrinking down the space of actions you do actually have to practically consider into something that's more tractable. And so now I'll actually talk about how do you define similarity beyond this like abstract notion. And the first is using sort of a performance base. And this is usually a pretty straightforward premise, which is just do two configurations have comparable performance, right? So if I have a given workload, and then if I sort of run that on a configuration A, configuration B, do they sort of yield similar metric data that the user cares about, right? So if the user cares about sort of like the runtime, do they have similar runtimes? If they care about transactions per second, do they have similar transactions per second, and so on. This usually is not practical at scale, just because there are a lot of configurations you do have to sort of look at. For each of those, running the workload starts becoming a pretty limiting factor. The fact that you have to like sort of actually deploy the config, then you have to like run the workload, you may have to collect the benchmark data. And so we often tend to use other various approximate measures. Some are sort of better than others, depending on sort of availability or like accuracy. So you could use the plan cost from the query optimizer. You could use sort of predictions from machine learning models if you have them available and they're actually accurate enough. Or you can sort of try and like estimate essentially query execution without trying to run queries to completion necessarily. And another method of defining similarity sort of revolves more on like a structural sense. And this is, in other words, really through domain knowledge rules, right? So these are curated by developers. They can come from support incidents. They could come from sort of just mass analysis of telemetry at scale. And these rules really just sort of make a judgment. So they don't necessarily say if it's true or not. There's just some judgment on like whether two things are sort of similar. And I'll provide two more concrete examples. The first is knob value bucketization. This is a trick that's commonly used in knob tuning in general. And so if you sort of take the value range that you could potentially set shared buffers to, a tuner that does not use bucketization will consider every value on this line that's valid. So it will consider 1 gigabyte, 1.1, 1.2, 1.24. With bucketization, what we really say is that values that fall in the same bucket, we basically treat them and say they're similar. And so that collapses them in a way to some discrete bucket. And so in this example, I've just sort of discretized them to 1 gigabyte. And so in this sort of setup, a tuner only just considers the discrete values, right? So it only thinks about 1 gigabyte, 2 gigabytes, and so on. Another more interesting or more abstract example is like we could have a rule that says indexes that share a prefix key are similar. And so in this sort of setup, if you have an index on A, an index on A and B, this rule would say they are similar just because they share a prefix. And the sort of intuition might follow just that for queries that you can use the first index for, you can probably also use the second index for. And then in the case of the second one, we have an index on A, B, and an index on B. The rule would say they are not similar by extension. So now let's sort of talk about more, I guess, interesting things about applying this technique, ProtoX to Postgres. I'm going to sort of start a bit with the reverse. I'm going to first just show more of like an experiment result and then talk a bit more about actually how we integrated some issues along the way. And the main thing here is just we run on Ubuntu 22. We sort of just have 192 gigabytes of RAM and SSD. This was run on Postgres 15. We mainly used two actually pretty important extensions to us. One was HypoPG for hypothetical indexes. And then PGConf.dev was also very crucial for doing query tuning. And we'd also have some more internal like extensions, some lighter patches into Postgres source itself, just to get us a little bit more sort of, I guess, like to get a bit more tuning, just to get a little bit more observability involved. And I'm mainly going to show results from the decision support benchmark. which was published from Microsoft, I believe, a year or two ago. And this is modeled off of TPCDS, the decision support one, for those more familiar with that. And it just simply adds a bit more sort of like skew, data skew, a bit more complex query types into the mix. And then I'll sort of show a comparison against several state-of-the-art tuners. These compose several specialized ones. So we start with PGTune, which is a heuristics knob tuner. We also include Dexter, which is a cost-based index tuner. DTA is the Microsoft Research's Anytime Database Tuner Advisor. So it does a cost-based search. And AutoSteer is a more recent one that sort of tunes query knobs, but with the notion of like by sort of using hint sets and trying to compose different hint sets together. And then I'll sort of compare also against two native composite frameworks. UDO is a hierarchical one that mainly targets knobs and indexes. And it's hierarchical because they split their tuning sort of allocation just based off of are actions heavy. So for instance, building an index, or are they light, which is like changing like the sequential page cost. And then I also compare against Unitune, which is sort of the turn-based scheduler I've been sort of describing at various points, where it picks the next tuner based off of benefit. Now I'll just show the actual evaluation. The main thing to note here is just the tuner runtime is on the x-axis. It is in hours. The y-axis is truncated. So the sort of there's a jump from 0 to 20, and lower is better. And so the y-axis will show the workload runtime of the best configuration discovered so far over time. And so since we do run each tuner about 4 times each, there's also going to be just a band of like the best and the worst in those 4 samples. So first I will show PGTune and Dexter. This is sort of like it's a very, very fast tuner. So this is the one that you would sort of tend to run if it's like, I need something that I can use in like a few minutes. And so this is sort of a very useful baseline to sort of compare everyone against relatively. Next, I'll show sort of UDO, which is the hierarchical knob and index composite tuner. As you can sort of tell from this graph, UDO does not actually do better than our baseline. And that's just because it misses sort of certain indexes that Dexter does suggest correctly. And this sort of reasoning here is sort of a twofold. One is just that it spends a lot of time executing queries in configurations that are suboptimal, right? So if you're in some configuration, they do still use timeouts, but they still end up spending a lot of time just running queries without sort of learning much from it. And the other sort of dual reason to that is just that it considers a lot of indexes, but it assumes every index is equally valuable to me. So there's no sort of sense of like, maybe I should use these indexes first. And so it just takes a long time for it to like identify what is actually relevant in that set and what is not. And then next I'll show Unitune, which selects the next tuner based on benefit. And as you can see here, it does eventually surpass the PGTune and Dexter, maybe about 6 to 8 hours in. But it does not substantially get much better over time. And this is a more reason just because the Unitune tends to start allocating more and more time as time goes on towards index and query tuning. And that's just because early on, that tends to be where you see the most benefit. So it naturally is like, I see benefit from doing this. I don't see much benefit from tuning knobs. So I'm just going to keep spending more and more time tuning indexes and queries. Whereas we do find at the end that it really should have spent time tuning knobs, like for instance, like boosting the amount of workers for like gather operations, and so on. And then next I'll show our more like interesting composite tuner, which is PGTune, Microsoft Research's Database Tuning Advisor, and AutoSteer. So that's this line down here. And it's sort of broken up into 2 segments. One is just that it drops down after 9 hours. That's when the index tuner finishes. And the second jump is at the 11-hour mark, give or take, which is when AutoSteer, the query knob tuner finishes. So and then it sort of just stays there for the rest of time. And then last, I will show our holistic tuner, Proto-X. Thank you. And so really what happens, as you can see in the shaded blue band early on, for the first 2 hours or so, it's really sort of spending time doing like initialization, setup, thinking, if you may, and then it just sort of quickly starts going down, converges, it starts basically plateauing around like 14 to the 16-hour mark or so. And we did inspect its behavior more closely and find that it does sort of recognize pretty early on that I maybe should have my knob set in this way. These indexes are probably going to be useful to me. And then it just sort of spends the remaining time after this sort of like steep drop-off area, usually just making smaller adjustments, sort of incremental changes to that. And so the sort of takeaway here mainly is just that ProtoX does find better configs. I'm going to sort of just clean this figure up a little, zoom in a bit to highlight that. So this is the sort of zoomed in figure. And the main thing here just to know is just that we get a further 78% reduction saving over PGTune and Dexter. And there is a 28% or so saving over PGTune, DTA, and AutoSteer. And the reason that this is sort of possible, one is just that ProtoX just tunes more variety than other tuners do. And so for sort of knobs, we currently sort of support tuning your system knobs. We can do table level knobs. We can do sort of index level ones. For indexes, we can handle arbitrary width. And so this arbitrary width may not sound super interesting, but it's a common limitation to a lot of these sort of academic tuners in that because of the way their encodings work and such, that they are sort of constrained to like 2 or 3 column indexes at best. And so we can also sort of pick the index type. So we can suggest whether it's a B tree, whether it's a hash index, whether you want to try Brin index. And we can also just handle sort of doing like include columns. And at a query level, we actually support quite a bit thanks to PGHint plan specifically. We can recommend sort of optimizer knobs. We can recommend hint at how should you access specific relations in a query. So do you want to scan this table with a sequential scan? Do you want to do a bitmap scan? Do you want to use an index scan? We can hint at for parallel scans. And we can also sort of hint towards materializing inlining CTEs conditionally. And beyond the variety supported, really, the other major thing is just that ProtoX considers these options together. Right, so just showing the decision support benchmark, it does have 49 queries for reference. And so I show some coordinating tuners, the number of system knobs, the number of indexes, query knobs, query hints they support. And so that's these two here, which is the hierarchical and term-based from earlier. And then now I show ProtoX. And the first thing I just want to sort of call out just to know is that we can consider the sort of limit in some ways of 141 trillion possible indexes. In addition, though, which is sort of more important, is that the hierarchical and term-based really consider these individually, right? So if sort of first thinks maybe I would look at my knobs, and then it sort of like locks them in, like puts them aside, and then it sort of moves on to the next thing that it wants to look at. And then it may come back and like look at it again later on. But in contrast, sort of ProtoX really looks at all of these like together. And so in getting this to sort of work with Postgres, we sort of ran into like 2 issues of sorts, if you may. The first revolves around sort of plan node timing. And as far as we're aware, this issue does exist in some forms in other systems and can be distilled down essentially to whether the reported operator time includes its children or not, is it complete or not. Our sort of workaround was just adding some additional timing just around each node's entry exit. There is also the commercial solution, PG Mustard, for those aware, that will fix up explain analyze plans. It will fix up your operator times if you just give them your plans. And the second more interesting issue is around execution. And this was motivated primarily by the fact that a tuner will make expensive changes, right? So it may try to build an index. Partition is another one that's sometimes expensive, is usually more expensive. And in some cases, you really don't want to actually go through the trouble of trying out this, like building out this change to then only just learn that like this actually does not help me at all. It was actually not a good use of my time. And so we sort of wanted to sort of find a way to just see, could we estimate a specific plan's runtime, assuming that you did have that change made, but just sort of using a different index under the hood, right? And the main thing is just like, we just want an estimate. So it's just some idea of, is this going to take 5 minutes? Is this going to take a minute, seconds? We don't necessarily care if it's going to take like the specific 1.4 or 5 seconds. We just want some idea. And so our slightly hacky-ish workaround was like, basically some work was in an extension, and we made sort of like 2 somewhat intrusive hooks just to the planner specifically around subplans. And those hooks really just gave us a little bit of extra control over like how Postgres actually creates the index scan, and also just allows us to reuse, piggyback off of a lot of the existing like index path logic, and so on. So to recap, just before we get into the final section, so with the holistic tuner now, we can sort of find more performant configurations compared to before, by just considering sort of orders of magnitude, more variety, more options than before too. So now I'm going to talk a bit about the future, sort of also discuss the recent advances in large language models, how that actually might factor into tuning. And so there's recently been a lot of interest to sort of apply the reasoning or capabilities of these language models towards the tuning context. And so to just sort of give a call out to Victor, he does have a paper published, I think, at Sigma this year, soon to present, that is sort of using language models for tuning. There's other work, I think, at VODB this year that's more focused on sort of using language models for knob tuning specifically. And the sort of high-level setup for this is just that there's some language model, and then they pass some prompt to it, right? So this prompt really just sort of describes what system is being optimized, what the workload might be, what query plans might be relevant, just additional context to provide, and some high-level instructions about what the language model should do, right? So in this case, it would be recommend some configuration parameters that optimize the system's performance. And then they really just sort of pass this into the language model and try and basically massage its outputs into something that we can actually deploy. So in this case, it would be maybe set shared buffers to a value. It might build indexes. And the other thing to note here is that this language model is not necessarily off the shelf. It can be fine-tuned. So you could actually reasonably conceive that we could, for instance, make it more Postgres specific if you if you give it the sort of mailing list data, the wiki, the manual, to just sort of help ensure that it will give you more likely it will give you more Postgres specific information and not some knob that you can only tune because Oracle has it, right? As a short aside, we did try actually fine-tuning an LLM with the mailing list. It does get pretty snarky pretty quickly, so there might be some controls you might have to do if you do that. And so for a sort of experiment to just evaluate, we use an identical setup to before. So same sort of Postgres 15, same instantiation of the decision support benchmark. And we'll sort of compare against Lambda Tune. Lambda Tune uses GPT-4o as its prompting backend. There is now been, I think, 03, 01 and such, so this sort of, I guess, dates this, this sort of, I guess, technique a little. And we also evaluate against the variation of sort of where we took Llama and then we fine-tuned it with historical data from Proto-X. And so that sort of forms a more fine-tuned language model variation. So once again, just the decision support benchmark. And for this case, the baseline I show here will be Proto-X. And then once again, lower is better. And so I'll first show Lambda Tune. And as you can see, it does end up finding configurations that are about 3.6 times worse. We looked actually a bit closer into what it was actually suggesting to just get an idea. And we found that in some cases, when you do ask it to suggest system knobs to tune, it will give you an Oracle knob. So that's slightly problematic. And then we also find that just because Lambda Tune does actually summarize the workload, so it does not pipe every single SQL query in to the language model. And so the configuration it ends up giving are just simply single column indexes on all the predicates in the summary. And next I'll show, which is fine-tuning on ProtoX data. This is much closer just because it has sort of just access to the ProtoX data more directly. But it still outputs configurations that are about 1.7 times worse, roughly. And without getting too much into the weeds, I'd be happy to sort of discuss this one a little more offline. But it's essentially just due to a matter of like prompting like focus, right? And so you can prompt these at a query level. You don't have to try to summarize the workload or put the whole workload through. You can ask it on individual queries, what should I possibly do? What's a good idea to try? The problem is that you then need additional sort of machinery to actually like validate those suggestions. You need machinery to help you actually compose them because it can suggest conflicting like system knobs depending on the query. It can suggest indexes. Then when you do build all of them in Postgres, it just degrades the plans. And so commonly we do end up just usually prompting with some workload just because it's sort of cleaner. It's usually more easier to like wrangle and deal with. But that does run into more like length, truncation issues. Like do you try and put every query through? Do you maybe only take the 5 most important queries that you care about? So that's sort of the reasoning there. So then I want to just sort of discuss what we are currently actively thinking about now, looking at. And the sort of high-level sort of summary of it all is like we're sort of looking at how we can accelerate sort of the discovery of interesting configurations. And there are some language models involved in this process. And the first part really is sort of just centered around learning from or adapting prior knowledge, right? And so most commonly, tuning is usually not a one-off operation. You will retune if like the workload changes, if the queries sort of change, the parameters have drifted in a way that now the system is not performing well. You might have new deployments. There's sort of new or migrations that require an initial round. And so in addition to this, also when you run a lot of tuners in different environments, you start accumulating a lot of sort of interesting knowledge that you can sort of start extrapolating from. And a common thing, for instance, is also just saying like if you start seeing workloads with similar characteristics, you can start saying stuff like, if they have this characteristic, maybe you should always apply these certain hints or these optimizations to it. If you have a query that accesses data in a certain style, then it may benefit from another hint or so. And so we're just sort of broadly looking at sort of different techniques, methods of sort of distilling or extracting like what is really important from prior experience to sort of accelerate the current like tuning objective, right? And so rather than needing like 14, 16 hours, as I shown before, maybe you can get much better configuration in just like an hour or 2 hours from this process. And to sort of do that, we are sort of looking at how sort of we can use these language models in a way to help identify what's relevant or not, what sort of might be missing, and like adapt the relevant aspects of it to the current tuning sort of context. Which is also more so perhaps relevant when like your schema doesn't match up exactly and sort of stuff like that. And the other angle we are sort of also pursuing a bit is sort of accelerating tuner setup. And this is sort of just driven by the observation that a lot of tuners may have an expensive query execution sort of setup phase. So they run like thousands of different queries just to get a sense of how do different operators work under different situations. How might the system behave under different situations? And so to that end, we have built a sort of a training data mode, if you per se may say, in Postgres. And so this is driven mainly just from the observation that as opposed to running regular queries where we actually care about what comes out, right? Like you don't want to be missing like a tuple when you really should have got it. Usually, tuners learn from the behavior of queries as they execute, right? So it's like, how do these certain scan operators behave under different circumstances? So they're less sensitive in a way to specifically, is this tuple there or not? And so we sort of just modified some executors to just allow for some sampling, some early termination. And so to sort of just bring it up to a wrap, if there's sort of anything to really take away from this, the first main thing is just that tuning holistically, so sort of considering all aspects of your system together at once is much better. than sort of alternate approaches where you sort of tune individual parts one at a time and try to compose it. And our tool sort of is the first to do this, as we're aware. And our holistic tuner sort of leverages action similarity to sort of reduce the effective search space and to make this sort of tractable. And just as a recap, we're sort of exploring techniques for accelerating tuners, whether it's sort of just adapting to new environments, changes in the environments, its speed or calibration. And we're also pretty intrigued by like the recent agentic capabilities of language models, like particularly like Claude 01 and such, and just like how they might play an active role in like adapting existing work, but also just discovering new configurations and how they might actually impact database tuning sort of as a whole. So thanks for listening, and open to any questions. I guess person in the back.
Yeah, okay. Firstly, really interesting, and been a lot of people have called it application DBA in the past. The thing is that most of it makes sense because a lot of the things I think we've done in the past but manually, and this is speeding it up. You did touch on it with the language models.
Yes.
Some of the stuff that's required, specifically in things like data warehousing, is specific to certain queries. And that's, I think, the nuances of sometimes having to think of the specific queries is not what you showed there. How does it manage with traditional large-scale queries that are needed for that sort of environment?
So that's, I think, so the question, if I understand correctly, is like, the data warehouses commonly have these queries that are like, I think, very different in nature. And so how do like sort of they, like language models might work in that sort of context?
That's not what I meant. No, because you're right up to love. It's not necessarily language models. It's just that they're specific for data warehousing and that individual query. While generically, what you might propose is specific generically for the whole system.
Right.
Rather than specifically the badly performing, the really badly performing query.
I think that's like something that it's not necessarily addressed directly by holistic tuning, but I think with like the right observability sort of into insight, coupled with like the right adaptive mechanism. So if you have known historical matching queries that might be interested that's sort of similar enough, then that's like I think the most rapid way you can actually target something that's like actually pretty important, but it's like not necessarily something that you will actually consistently like be able to like execute repeatedly in your environment sort of safely. Yeah. Yeah. So it's, yeah, that's like something we're sort of very in the current active sort of stuff thinking about. There's still yet to be a very solid, definitive like answer of like what you should do or what you should not do at least. Yeah. So.